Acid-base properties of ions and salts. That's not a good sign. Whatever. Some ions act as bases because they are the conjugate bases of weak acids. Right? So if we look at this, this is the hydrogen carbonate ion. That's an ion, but it acts as a base. You react it, or you put it in water, and it can accept a hydrogen ion from the water to produce hydroxide ions. What does it form here? Carbonic acid. This is the conjugate base of a weak acid. Because this is a weak acid, the conjugate base is a weak base, right? It's important to remember that anytime you have an ion in solution, like this hydrogen carbonate ion, there has to be a counter ion. You can't have a solution of just negative ions or just positive ions. There are other ions there. Those are called counter ions, the one that counters the charge. So it forms a salt, an ionic compound. Soluble salts dissociate in solution. So here we have sodium hydrogen carbonate, or sodium bicarbonate, baking soda. That dissociates in water to form sodium ions and hydrogen carbonate ions. So there are sodium ions present, but they are not doing anything in terms of acid-base activity. But a solution of sodium hydrogen carbonate will be basic because this is the conjugate base of a weak acid. So it can act as a base. Any questions? Okay, so let's look at anions. We can think of any anion as being the conjugate base of an acid, right? Because you've got an anion, if you stick a hydrogen ion on it, you've got an acid. So in general, we say, well, A minus, that's going to be the conjugate base of the acid HA. Okay with that? So nitrate ion, that's the conjugate base of nitric acid. Sulfate ion would be the conjugate base of sulfuric acid. But not every anion acts as a base. We can think of it as a conjugate base, but it may not actually have any base qualities. It may not make the solution basic. It depends on the strength of the acid that it is the conjugate base of. If the conjugate base is related to a weak acid, then it will be a weak base. If it's the conjugate base of a strong acid, then it's pH neutral. It's not going to have any effect. So let's think about that. So HCl is a strong acid, right? You put that in water, it ionizes completely. So chloride ion is an anion. We can think of it as the conjugate base of this acid. But is the reaction where Cl minus accepts a proton to form HCl actually going to happen in solution? No, because it only goes in this one direction. The strong acid ionizes completely. The reverse reaction just doesn't happen. So chloride ion is said to be pH neutral. It's not going to affect the pH of the solution. Oh, look, I did that. What about the fluoride anion? Well, that's the conjugate base of HF, which is a weak acid. So this weak acid ionizes partially. This is an equilibrium. So if I have fluoride ion, it can act as a base, accepting a hydrogen ion, and form HF. This is an equilibrium. It goes both ways. And so the conjugate base of a weak acid is a weak base itself. Sounds like I'm talking in circles, doesn't it? Feels like I'm talking in circles. Here's a graph for figure. It's a figure. So up here we have strong acids. Those are some of them. And these are the conjugate bases of those strong acids. So HCl, you take the H plus away, you've got Cl minus. So these ions here are considered neutral because they don't accept protons and form these strong acids. Down here we have strong bases. There we go. Down here, these are strong bases. And so their conjugate acids are also neutral. And in between, we have weak acids and weak bases. And the stronger an acid it is, the weaker the base, and vice versa. Okay, so classify each anion as a weak base or pH neutral. So CHO2 minus. Well, what's the acid that this is a conjugate base of? We just put an H plus on the ion, right? So HCHO2. And then ask yourself, is that a weak acid or a strong acid? It's a weak acid. Because it's not one of the 6 you're supposed to memorize, right? Do you need to know its name? No. It's just not hydrochloric, hydroiodic, hydrobromic, perchloric, nitric, or sulfuric.
And do we also need to remember the strong bases as well? Or just strong acids?
You should know the strong bases as well. Those are actually even easier. Metal hydroxides, right? Group 1 and 2. So calcium hydroxide, strong base. Sodium hydroxide, strong base. Anything else? Not, right? Ammonia, methylamine, dimethylamine. It's not a metal hydroxide, it's not a strong base. So if this is the conjugate base of a weak acid, is it going to act as a weak base? Yeah. So this is a weak base. How about perchlorate ion? What's the conjugate acid? HClO4. Strong or weak? Strong. This is a strong acid. The anion then is pH neutral. Do you understand why it's pH neutral? So if we look at perchloric acid ionizing, right? It ionizes completely. If this is going to function as a weak base, it has to be able to do this. It has to accept a proton. Oh. But is it going to do that? No, because this reaction goes to completion. It does not go back. So this cannot act as a base. It will not accept a proton. So the other part, the conjugate base or the conjugate acid from a strong base or I know what I'm trying to say. From a strong acid or a strong base will be pH neutral because they react completely. So let's look at anions that do act as weak bases. So we can figure out the pH of the solution in which we have an anion acting as a weak base, but we have to know what that Kb is. Well, if you're looking for this, you're going to find Kb's for things that are neutral molecules that are weak bases, but you're not going to find tables of Kb's for anions. So we figure it out from the acid dissociation constant, the Ka. So here we're asked to derive the relationship. Okay, so I'm going to show you this. So here we have an acid dissociating. So I'm going to write the expression for Ka. So Ka is going to be hydronium ion concentration times the concentration of A minus divided by the concentration of HA. The water gets left out because it's a liquid, its concentration can't change. Over here, I have the chemical equation for the anion acting as a base, accepting a proton from water to form hydroxide ion and the weak acid. So that's the expression for Kb. So that would be OH minus times HA divided by A minus. You okay with those? So let's multiply Ka times Kb and see what we get. So there's Ka and Kb. So that's a mess. But there's some things that we can cancel out. So A minus occurs in the numerator and in the denominator. HA occurs in the numerator and the denominator. What are we left with? H3O plus times OH minus. What is that also known as? KW, right? So Ka times Kb equals Kw. What's the value of Kw? 1 times 10 to the minus 14. So if you know one of these, you can find the other. And that's why they don't make tables, because you can calculate it if you need it. Any questions? So up here in the box, you should remember this. Determining the pH of a solution containing an anion acting as a base. Okay, so find the pH of a 0.250 molar sodium acetate solution. Well, let's look at the chemical equation for this acting as a base. Is this sodium going to do anything? No. So let's leave it out. It's a spectator ion. It's going to make things muddy. So we're going to leave it out. So we've got C2H3O2 minus. And when this is acting as a base, if we look at it interacting with water, acting as a base, it's going to accept a proton. So it's going to be HC2H3O2 plus hydroxide ion. Okay with that? So what are our initial concentrations here? What's the initial concentration of acetate ion? 0.250. This is a soluble ionic compound. It completely dissociates, and so the concentration of the acetate is the same, 0.250. Water is a liquid. We don't have to worry about it. What's the initial concentration of acetic acid? 0. How about the hydroxide? 0. There's a little bit from the water itself, but probably too small to matter. So then in our change, this is going to change by minus x. This is going to change by plus x. This is going to change by plus x. Because this is a base, this is Kb. So Kb equals x squared over 0.250 minus x. But we're stuck now, aren't we? They didn't give us KB. Well, this is acetic acid. It's a weak acid. We can find a table and look up the Ka. It's a lot of scrolling.
It's one of these on the homework that I was like, what the? I had to look it up.
Yeah, you got to look it up.
You got to look it up, and I was like, oh, that's.
Well, actually, here's acetic acid. I mean, you can find it in a table, but I just happened to find it here sooner. It's 1.8 times 10 to the minus 5. Now, I'm not going to make you memorize any of the Kas. The only thing you should memorize is Kw is 1 times 10 to the minus 14, because that one gets used all over the place. The rest of these, it'll either be given in the problem on an exam, or I'll give you a table that you can look it up in. On the homework, you know, you've got your book, you've got resources. Go look it up. Okay, so let's see if I can remember this. 1.8 times 10 to the minus 5. So this equals 1.8 times 10 to the minus 5. Does it? This is Ka. What is this expression for? Kb. Oh, wait a minute. So I can't do that. I have to figure out what Kb is. Well, Kb equals Kw divided by Ka. So I've got 1 times 10 minus 14. I'd like to say I did that just to try to trick you, but I actually started tricking myself. I caught myself before I finished it, though. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. 5.6 times 10 to the minus 10. I've hammered significant figures into students so long that this 2 sig fig thing just drives me bananas. We can end up with some rounding errors very easily, because what my calculator is saying is 5.5555555. So what I'm going to do here is what I teach my 1A students to do. So yeah, it's got 2 significant figures. Write down 2 extra digits, and that will avoid rounding errors. You don't even have to worry about rounding the second one. Just write down the 2 next numbers and carry those along. And that is a 10 and not a 6. There we go. So that is Kb. Well, let's try x is small, because that's been working pretty well for us, right? So x is small approximation. We're going to get Kb, the square root of it, times 10 to the minus 10. And then we've got that denominator, 0.250. And that's all under that square root thing. So x is essentially 1.2 times 10 to the minus 5. That's going to be okay, but let's double check anyway. Divide by 0.25, and this is like way under 5%. So x is small is valid. We found x. What were we trying to find again? The pH. Oh, yeah, that's right. Okay. So for pH, X is going to give us the hydroxide ion concentration, right? So I'm going to change colors here because this is getting messy. Hydroxide ion concentration equals 1.178 times 10 to the minus 5. So the pH then is going to be, pH is going to equal 14 minus the pOH. So 14 minus the negative base 10 log of 1.178 EE minus 5. 9.07. You got 9.25? Well, the book got what I got. So I'm gonna stick with my answer here. I'm kind of curious, what if we round that? Does it make a difference? You got it? Yeah, well, it makes a difference if you leave the log out. That's comes out really weird. So if I rounded that to 1.2, then my calculator is saying 9.079, which would round to 9.08. Smidge different, not super significant. Any questions? Yeah.
After you got to get to the KB, why did you get the KB?
I needed the KB because I've got this anion acting as a base, so it's accepting a proton, giving me an acid plus hydroxide. So when I do this ice table and do the products over the reactants, this is KB, not Ka. And so I need to find out what Kb is, and the way I do that is from the Ka, Kw divided by Ka. So this is the number that I stick in over here. Any other questions? Finding the pH of a weak acid solution. Wait a minute. Okay, I know what happened. I scrolled back. I'm like, well, that looks familiar. That's the one we just did, right? Okay. So anions can act as weak bases. Cations can act as weak acids. There's three categories of these, just like with the others. So we've got cations that are counterions of strong bases. So these are going to be pH neutral because those strong bases dissociate completely, so their counterions cannot ionize water. So these are the calcium, strontium, barium, lithium, sodium, potassium, the group 1A, 2A metals. It's the cation from a strong base. Doesn't do anything. Then we've got cations that are conjugate acids of weak bases. So here we have the conjugate acid of a weak base. So this could be something like ammonium ion, right? We've got our weak base. It accepts the proton. Now it becomes a conjugate acid. So this can now donate the proton back to water. So it can act as an acid. That cation that is a conjugate acid of a weak base is a weak acid. And the pH of the solution can be calculated using Ka. Because this is the cation, the conjugate acid of a weak base, the table's going to show us Kb. And then we have to use Ka times Kb equals Kw. It's like alphabet soup in here, right? Another type of cation that can act as an acid is small, highly charged, there's another typo, highly charged metals like aluminum and iron. So aluminum has a positive 3 charge, iron has a positive 3 charge. And we look at those in the periodic table, and they're in the third and the fourth period, so they're among the smallest of the metals. They have higher charges, though, than something like lithium. So these ions can become hydrated, so the aluminum can gather 6 water molecules around it and form this complex ion. We'll learn a lot more about complex ions later. So here we've got this complex ion, the aluminum with 6 water molecules around it. This can act as a Bronsted-Lowry acid, donating one of its protons to a water molecule. So here we've got this aluminum with the 6 waters, and one of the hydrogens from the water can go onto a regular loose water molecule, and now we've got this ion. So we have one hydroxide in there, and the rest are still water. So that can happen. Okay, classify each cation as a weak acid or pH neutral. So lithium ion, that is the counter ion of the base lithium hydroxide. Is that a strong base?
Yes.
Yeah. So does lithium act as an acid? No, it doesn't, because it's pH neutral, because the lithium hydroxide dissociates completely. Lithium is not going to take anything back. So this is pH neutral. How about this one? What does that look like? Does it look a little bit like that? Oops. So, or we could maybe write it like this. So this is one of those amines that has functioned as a base, it's accepted a proton, and now it's become the conjugate acid. It's a cation. So the amine, is it weak base or strong base? It's a weak base. So if this came from a weak base, can it act as a weak acid? Yeah. And then how about iron 3 ion? Can that act as a weak acid? Yes, because the previous slide. So iron ions, iron 3, and aluminum, those can act as acids. Questions? So if we look at salt solutions, the pH of the salt solution is going to depend on the specific cation and anion that are involved. So if you have salts where neither ion acts as an acid or a base, then you're going to have a pH neutral solution. So this is going to happen when the cation is a counterion of a strong base. The anion is the conjugate base of a strong acid. So sodium chloride. Sodium is the conjugate acid of sodium hydroxide, a strong base. Chloride is the conjugate base of hydrochloric acid, a strong acid. So you put salt in water, it doesn't change the pH of the water at all. These are pH neutral. A salt where the cation does not act as an acid, but the anion acts as a base. Well, this is going to make a basic solution, right? So here you've got cation comes from a strong base, anion comes from a weak acid. We're going to have a basic solution. And then we've got the opposite. The cation acts as an acid, the anion does not act as a base. So this is going to be an acidic solution. So here, the cation is going to be the conjugate acid of a weak base, or it may be a small, highly charged metal. And then the anion is the conjugate base of a strong acid. So FeCl3, here we've got this small, highly charged cation that can get water molecules and then donate hydrogens from those The chloride, though, is the conjugate base of hydrochloric acid, so it doesn't do anything. What if both the cation and the anion are functioning as acids and bases? Well, then we need to look at the relative strengths of the Ka and the Kb. And the higher K value is going to dominate. So there is a little table that summarizes all of that. And then let's practice a little bit here. So here we have ionic compounds, and we're trying to figure out if the solution is going to be acidic, basic, or neutral. So sodium hydrogen carbonate. The two ions we've got there are sodium and hydrogen carbonate. Slap a hydrogen on this one, and what do you get? You get H2CO3. Is that a strong acid? Is it one of the six? No, this is weak. That's a weak acid. So does this act as a base? Yes. So this acts as a weak base. What about the sodium ion? Well, slap hydroxide on that. What do you have? Strong base. So this is a strong base. Sodium isn't going to do anything. So the hydrogen carbonate ion acts as a weak base, so this solution will be basic. Well, this mess. Well, do you see the N hiding in there? In here. So that's like NH3 with something hanging on it, plus and a Cl minus. So this is the conjugate acid of a weak base. Amines are always weak bases. So the conjugate acid acts as an acid. Chloride is the conjugate base of a strong acid, HCl. So the chloride's not going to do anything. So this is going to be what? Acidic. Because this can donate its proton and reform the weak base. The equilibrium goes both ways. How about this one, KNO3?
Hold on. That one, I missed it.
This one?
Yeah. Cl is.
The Cl, its corresponding acid is HCl, which is strong acid, right? So strong acid, this is the conjugate base. It's not going to act as a base. This is the conjugate acid of a weak base. And so it can donate the proton back to water, say, I'm done with it, and reform that base. So it can act as an acid, and it will. Potassium nitrate, we've got potassium ion. Think, well, what if we put hydroxide with that? Strong base, so that's not going to do anything. Nitrate ion, put a hydrogen ion on that. Nitric acid, is that a strong acid? Yep. So this one is pH neutral. It's not going to do anything.
There's a strong acid and a strong base.
Yeah, because we got the conjugate base of a strong acid and the conjugate acid of a strong base. And so they don't do anything. And then this guy down here, FeNO33. Well, we got iron 3 ion and nitrate ion. Well, we just looked at nitrate ion up here, right? And said it didn't do anything because nitric acid is strong. So that doesn't do anything. What about the iron? Acts as a weak acid. So that one's a little bit harder to understand, right? So think of it this way. So you've got ammonia and ammonium. This is the base. This is its conjugate acid. cations can only, I did finish it. It's just not showing up there. So the cation is the acid. Cations can only act as acids, they can't act as bases. So when we're looking at this, I can remember, okay, iron 3+ and aluminum 3+, they do something. But then I have a hard time remembering what they do. They do what other cations do. They can act as acids. Oh, I didn't finish it, did I? Psst. Yes, so this will be acidic.